Hello everyone again. Just now we are going on our virtual congress again. This presentation is going to be a pre-recording from Dr. Michal Horak. Michal Horak is going to present his presentation. Dr. Horak, do you hear me?
Yes, I hear you.
Yes. Fine, thanks. What about you?
Oh, fine.
Okay. Thank you. First of all, I want to thank you to be a part of this conference, to attendance this conference with your pre-recording. In a few minutes, I am going to start your pre-recording. End of your presentation. If there's any question, is there any question? We can take the questions from the chat part, and you can answer them. Okay?
Yes, I will answer them after the presentation.
Okay. Thank you. Just now. Okay. Just now, I am starting Dr. Michal Horak's presentation. He's joined us from Brno University of Technology, Czech Republic, as an invited speaker. His presentation title is Electron Microscopy and Spectroscopy in Plasmonics. And also, we are going on the recording. Yes.
With a brief introduction, to plasmonics, electron microscopy and spectroscopy. Good morning, ladies and gentlemen. Welcome to my presentation about electron microscopy and spectroscopy in plasmonics. I will start with a brief introduction where I introduce to you plasmonics, electron microscopy and spectroscopy and its application in plasmonics, and I will tell you what does the electron energy loss spectroscopy see. I will continue with a short example of what all we can analyze by analytical transmission electron microscopy in the field of plasmonics, and I will illustrate it on silver amalgam nanoparticles. Then I will discuss experimental aspects of our work. It means the fabrication of plasmonic antennas and the influence of experimental parameters on plasmon measurements by EELs. The last part of my talk will deal with imaging of electric and magnetic near fields by electron energy loss spectroscopy in plasmonics. I will tell you there few words about Babinet's principle in plasmonics, and then I will end up with electric and magnetic near field measurement by EELs. So let's start with the brief introduction. Plasmonics deals mostly with surface plasmon polaritons, which are collective oscillations of free electrons at metal dielectric interfaces connected with the local electromagnetic field. Localized surface plasmons are then surface plasmon polaritons, which are confined in a metallic nanoparticles in the form of standing waves, and their characteristic feature is local confinement and enhancement of the electromagnetic field. They have wide field of applications in, for example, in communication technologies, sensorics, medicine, energetics, and it can be illustrated by a microscope coming from 4th century, or to biosensors, which are typical example from 21st century. Electron microscopy and spectroscopy in plasmonics can provide many useful information. When the primary electron beam hits the sample, a lot of different signals came up. First, several electrons are transmitted, and they can be scattered either elastically or inelastically. Elastically scattered electrons and unscattered electrons can be used for imaging up to atomic resolution. Inelastically scattered electrons are used for electron energy loss spectroscopy, which can be useful for plasmon measurements with a nanometer spatial resolution and with the energy resolution of approximately 100 millielectron volts. Additionally, we can do chemical analysis of the sample, and we can measure the thickness of the sample. Another very useful signal are phonons, either light energetic, it means infrared, visible, and ultraviolet light, which is detected by cathodoluminescence, and by CL we can measure radiative modes of localized surface plasmon resonances. We can measure them with a nanometer spatial resolution and with the energy resolution of approximately 10 millielectron volts. Another part of useful phonons are X-rays, and with energy dispersive X-ray spectroscopy, we can do the chemical analysis of the sample. So the key technique for this talk would be the electron energy loss spectroscopy, which measures the energy distribution forwarded to the particle by the electrons to induce some excitation. And this excitation can be, for example, the localized surface plasmon resonance. The signal in this case is proportional to out-of-plane electric field. So what all we can analyze by analytical transmission electron microscopy in plasmonics, we will illustrate it on silver amalgam nanoparticles, which we have studied last year. So silver amalgam is one of the most suitable solid electrode material in electroanalysis of various reducible organic and inorganic compounds. And nanostructuring the silver amalgam promises improved electrochemical performance, and it brings along the prospect of plasmonic activity. Nanoparticles can be prepared by electrodeposition on indium tin oxide support for a mixed solution of silver and mercury ions, and then these nanoparticles were transferred onto a silicon nitride EM membrane to do our analysis. So first, we find out that the silver amalgam nanoparticles are polycrystalline, which is proved by this selected area diffraction pattern recorded on this silver amalgam nanoparticle. Then we do the chemical mapping by STEM EDS, and we find out that the silver amalgam nanoparticles are a homogeneous alloy of silver and mercury, and there are no other contaminants. The only additional signal comes from silicon and nitrogen, which corresponds to the silicon nitride EM membrane. Then we measured the plasmonic activity of these nanoparticles by electron energy loss spectroscopy. On the right side, you can see the investigation of a rod-shaped nanoparticle where we detected 3 different modes. The first mode is longitudinal dipole mode at 1.7 electron volts, so it is the energy corresponding to the first peak in ILS spectra, and it corresponds to the oscillation of charge along the long axis of the structure. The second mode corresponds to the transversal dipole mode, and it's at approximately 2.8 eV. So this corresponds to the second peak in ILS spectra. And then we have there also third peak at 3.2 eV, which corresponds to quadruple mode. So we found out that these silver amalgam nanoparticles are plasmonically active. It means they support localized surface plasmon resonance. And the important result is that the dipole plasmonic resonance can be tuned by changing the particle size from ultraviolet to infrared spectral region. So this opens the possibility to combine plasmonics and electrochemistry together in the future. Now let's move to experimental aspects of our work. So first, we did a comparative study of plasmonic antennas fabricated by electron beam and focused ion beam lithography. We found out that both techniques are suitable for fabrication of plasmonic antennas, but we have to say that electron beam lithography should be prioritized as the quality of resulting antennas is better, meaning that they have lower contamination and stronger plasmonic response. On the other hand, focused ion beam preparation of plasmonic antennas have worse quality of resulting antennas. These antennas have smooth edges and pronounced variations in thickness, and they are contaminated by carbon, gallium, and oxygen, and their plasmonic response is lower. On the other hand, we have to say that EBL fabrication is more complicated because first you have to coat your membrane with resist, then do the EBL and development, then you deposit the metal, and at the end, after lift-off and cleaning, you have your sample ready. Whereas in the case of FIP, you simply deposit metal on your membrane and do the ion beam milling. So it means for small series of antennas, the FIP preparation is much faster, and if you optimize it, it might be the quality of resulting antennas might be satisfying for you. So now let's move to the most important question for all electron microscopists. So what are the optimal STEM ILS experimental parameters to measure plasmonic resonances? So the main critical parameter is primary beam energy, which can be either low, medium, or high, depends on which TEM you have. So in the case of low energy, in our case, it was represented by 60 kilo electron volts. We get the highest signal, here shown by the blue line, but the raw spectra had large background. You can see this blue dashed line, and this background is mostly due to large elastic scattering in the sample, which results also into noisy spatial maps. So 60 kV in our case was good only to get the highest signal, but as the background was too high and the maps were really noisy, we said that 60 kV is not a good primary beam energy for STEM ILS experiments in the field of plasmonics. Then, if we take into account high primary beam energy, it means, for example, in our case, 300 electron volts, we see that the signal is lower than at 60 kV, and we see also that the background is still high. In this case, the background is not high due to scattering, but due to relativistic effects. It means the speed of the electron in material is higher than the speed of the light there, and chunk of radiation is excited there. On the other hand, at 300 electron volts, you have little difference in the relative thickness of your sample, and this results into spatial maps with lowest noise. So the choice of this high primary beam energy is very useful when you need to do good spatial maps of your plasmon modes. The optimal signal to background ratio is reached when a medium primary beam energy is used. It means it's a compromise between elastic scattering and between relativistic effects. So in this case, you have the lowest possible background, as the scattering is suppressed because the primary beam energy is as high, but in the same time you have the background as low because the primary beam energy is as low as the relativistic effects are still negligible. So this compromise primary beam energy seems to be the optimal for imaging plasmons by electron energy loss spectroscopy. Now let's move to the final part of my presentation, which deals with imaging of electric and magnetic near fields by EELs in plasmonics. So let's start with Babinet's principle, which comes from theory of optics and diffraction, and originally it says that diffraction patterns from an opaque body and from a hole of the same size and shape are identical, except of the overall forward beam intensity. This principle was formulated by Jacques Babinet in 19th century. In plasmonics, Babinet's principle of complementarity says that in the case you have infinitesimally thin and perfectly conductive metal, particles and apertures have similar plasmon energies. So and the spatial distribution of electric near field of the aperture corresponds to the magnetic near field of the particle. We did a study on disc-shaped antennas, and when you want to move from particle to aperture, you have to swap electric and magnetic fields. It means in the case of particle, you have electric field. Here is plotted EX and EY. It means the in-plane components of the electric field. So you have to swap to magnetic field and swap polarization. So EX is corresponding to HY in the case of aperture, and you have to rotate by 90 degrees and possibly to multiply by -1. And we can see that qualitative correspondence is very good, but on the other hand, we see that we have stronger fields for particles and electric component. So the Babinet complementarity is not 100% perfect in the visible range. Another thing which is very useful with Babinet principle in plasmonics is interchanging electric and magnetic field hotspots in the case of bow-tie and diabolo antennas. So the basic bow-tie has an electric hotspot. Basic diabolo has magnetic field hotspot. And if you made inverted antenna, you have inverted bow-tie with magnetic field hotspot and inverted diabolo with electric field hotspot. So you can play with changes between electric and magnetic field hotspots and between particles and apertures. So you can choose easily what you want for your applications. For example, for good transmissivity, you take probably particle antennas. For good reflectivity, you might want to take aperture antennas. And for all designs, means for both particles or apertures, you are able to get both magnetic or electric hotspots. So what all you have to do when you want to image electric and magnetic near field in a plasmonic antenna by EELS. First, you have to identify your plasmon modes in your structure. So first we take the structure, in our case diabolo and inverted diabolo, and record EELS spectra at specific positions which are marked in the figure by colored squares. We see that in both antennas we have 4 peaks in the EELS spectra, which correspond to 4 different modes. These modes are at similar energies for both antennas, means the first peak in the case of diabolo is approximately at 0.7 eV, and the first peak in the case of inverted diabolo is also at 0.7 eV. It means we have the same mode in 2 complementary structures. If we want to measure electric near field by EELS, we take our structure, means the diabolo, and we record the EELS map for a specific plasmon mode, in our case for the first peak, which corresponds to longitudinal bonding dipole mode. The signal is proportional to out-of-plane electric field, so bright spots in the EELS map correspond to antinodes of charge oscillations, and they correspond to maximum intensity of electric field, the out-of-plane component. We note that with this alignment, EEL is blind to in-plane field, so electric hotspot cannot be imaged. So this is how we simply can image the out-of-plane electric near field by EELS. But what we have to do when we want to image magnetic near field by EELS? Can we measure it? Basically, no, because EELS is insensitive to magnetic field. But we have the trick with Babinet's principle, because Babinet's principle allows us to swap electric and magnetic components. So if we want to measure magnetic field in the particle antenna, it means in the diabolo, we have to measure EELS in the inverted structure, it means in the aperture. We do the same, so we record EELS map, which is energy filtered at the energy of the first mode, and this signal is proportional to the out-of-plane electric field of the aperture, and this corresponds to magnetic field in the direct structure. So now we have correspondence between EELS on inverted structure and out-of-plane magnetic field on direct structure. So this is the way how to image magnetic near field by eels. And this we can repeat for all 4 modes. So it means in the case of diabolo, we have longitudinal bonding dipole mode, its electric near field, and its magnetic near field. Then we have the same for transversal dipole mode, again, electric near field of the particle and magnetic near field of the particle. And the same we have also for other 2 modes. It means for longitudinal antibonding dipole mode and hexapolar quadrupolar mode. So this is the easy strategy how we can indirectly measure the magnetic field of a particle by measuring electric field of the aperture. So let's move to conclusion. So during my talk, I have shown you what all we can analyze by analytical transmission electron microscope in plasmonics. I illustrated it on silver amalgam nanoparticles. Then I discussed experimental aspects of our work on a comparative study of plasmonic antennas fabricated by EBL and focused ion beam. Then I discussed influence of experimental parameters on localized surface plasma measurement by electron energy spectroscopy, showing that we need a compromise between elastic scattering and relativistic effects. So the best way is to use middle primary beam energy. In our case, it was 120 kV. And then I was talking about imaging of electric and magnetic near fields by eels. To this, we need to use a trick with Babinet principle in plasmonics, which allows us to swap between electric and magnetic field when we go from particle antenna to aperture antenna. And by this trick, we can image the magnetic field by eels, which is sensitive exclusively to electric field. So again, we have diabolo and in this case transversal dipole mode. Here we have simulated electric out of plane field and magnetic out of plane field. And if we measure, if we get the EELS map of direct structure, we have very good correspondence with the EZ simulation. And if we get the EELS map of inverted structure, it means of the aperture, we have very good correspondence with EZ. So that's all from my side. I would like to acknowledge and to thank all my collaborators and other colleagues, and also agencies and institutions for the support, and you for your attention. Thank you.
Yes, Dr. Michal Horak, thank you for nice presentation and nice research. Just now.
So if there are any questions, I will be happy to answer them.
Yes. In a few minutes, we can wait to our participants. Is there any questions or not? If any participant want to ask questions, we can open your sound from the host system. But first of all, please write the chat section. You have any question or not? I think that there is no question for now.
Okay.
If any participant want to ask any question, you can send an email Dr. Horak about his nice presentation. Dr. Horak, thank you again. Be a participant and join at the attendance at this virtual conference again. Thank you so much.
Thank you. Bye bye.
Bye bye.